Hello everyone and welcome to the third video. In this video I'm going to use another example in which the molar ratios are not 1 to 1 to 1 as stated previously. And we will learn how to determine a bond enthalpy when we are given the enthalpy change of formation of a reaction which is listed here. In this example, 1 mole of Br molecules reacts with 3 moles of fluorine molecules to form 2 BrF3 molecules, all of which are in the gaseous state, and thus bond enthalpies can be used to determine the bond enthalpies in this case. We are given this enthalpy change of reaction as listed here as negative 545 kilojoules per mole. Thus, we have the value for this arrow, and we are asked to calculate the BRF bond enthalpy. In this example, we are asked to calculate the BRF bond enthalpy, which we are not given. We are only given the bond enthalpy for a BR bond and an FF bond. Thus, the first thing I would do is I would draw these molecules. So I have Br bonded with another Br here, 1 mole. Thus, I have one molecule, one gaseous molecule, and I have 3 F2 molecules. Thus, I have 1 molecule, 2 molecules, 3 molecules of F2 in the gaseous state over here. And I have 2 BrF3 molecules. BrF3 is drawn as such. And I have 2 molecules of, 2 molecules of BrF3 in the products. And I have the value for this arrow over here, which is negative 545. Thus, the first thing we would do is I would place a box here with all the gaseous atoms in either the reactants or the product, since they are the same. I have 2 Br gaseous atoms here, and I have 6 F gaseous atoms. Now I can link the cycle by breaking the bonds in both the reactants and products. Thus, this arrow over here would represent the enthalpy change required to break 1 mole of Br-Br bonds, which is positive 193. This arrow over here represents the energy required to break 3 moles of fluorine-fluorine bonds. Per mole of fluorine-fluorine bond, the bond enthalpy is positive 158, and thus this value would be multiplied by 3. And then I have the energy required to break these 2 products over here. I have 6 BRF bonds in total, 1, 2, 3, 4, 5, 6 that required breaking. Thus, and this is the value we are asked for. Thus, this would represent 6 BRF. Thus, I would place it as 6x. And the next step would be to solve for x by moving through the cycle from the reactants to the products, which produces this value over here. Thus, this would translate, or simply using the general equations listed previously, which is the enthalpy change of a reaction we stated previously, determined using bond enthalpies, would equal the sum of the bonds broken in reactants subtracted from, to change the sign of this, because we're going to move from reactants to products through the cycle, so we would move with these 2 arrows, but we would move against this arrow, and thus this sign needs to be changed, and this is why this negative sign is placed here. Subtracted from the sum of bonds formed in products. The enthalpy change of the reaction is given as negative 545, which equals to the sum of the bonds broken in the reactants, which is positive 193, plus 3 multiplied by positive 158, and then I would subtract it from the sum of the bonds formed in the products, which is 6x in this case. And we would solve for x to determine the value of the BRF bond enthalpy. The answer for this question would be positive 202. Once you work out x, x would equal positive 202 kilojoules per mole. And obviously, since they asked for enthalpy, bond enthalpy, it should be, your answer should be positive, because bond enthalpies are defined as bond breaking, which is an endothermic process. Thus, if you're asked to calculate the bond enthalpy, your answer should always be positive 202. Thus, to sum up what we learned in previous lessons regarding calculating enthalpy changes of reaction by constructing energy cycles in subtopics 5.2 and 5.3. Thus, if we were given enthalpy changes of combustion values, which are listed in table 13 of the data booklet, the enthalpy change of reaction is calculated as the sum of the enthalpy change of combustion of reactants subtracted from the sum of the enthalpy change of combustion of products. While if you're asked to calculate the enthalpy change of reaction when given enthalpy change of formation values, which are listed in table 12 of the data booklet, the enthalpy change of reaction would equal the sum of the enthalpy change of formation of the product subtracted from the sum of the enthalpy change of formation of reactants. While if you're asked to calculate the enthalpy change of reaction occurring in the gaseous state using bond enthalpies, which are listed in table 11 of the data booklet, the enthalpy change of reaction is calculated by the sum of the bonds broken and reactants subtracted from the sum of the bonds formed of products, as we discussed in videos 2 and 3. One common question that you will get in the IB regarding bond enthalpies and the enthalpy change of formation and combustion values, you would be given a question, and in the first part of that question you would be asked to calculate the enthalpy change of the reaction using either enthalpy change of combustion or enthalpy change of formation values using the equations listed here. In the second part of that question, you would notice that all the reactants are in the gaseous state and the end products are in the gaseous state, and thus you will be asked to also calculate the enthalpy change of the same reaction using bond enthalpies this time. And you would calculate it as shown in this equation here. The third part to that question would ask you why the two values differ. The two values would differ because enthalpy changes of formation calculated using bond enthalpies are less reliable than those calculated using experimentally determined values such as enthalpy change of combustion or enthalpy change of formation values, because they are average bond enthalpies, which are averaged over several similar compounds as discussed previously. So you'd always get a question in which in the first part you'd be asked to calculate the enthalpy change of the reaction using either enthalpy change of combustion or formation values, which are experimentally determined and accurate. The second part would involve you calculating the enthalpy change of the same reaction using bond enthalpies. And the third part of that question would ask you why those two values differ, and your answer would always be in terms of bond enthalpies being average bond enthalpies, which are averaged over several similar compounds, and thus would produce somewhat inaccurate results. Thus, the enthalpy changes of reactions calculated using experimentally determined values such as enthalpy change of combustion and formation values are always more reliable and more accurate than those determined using bond enthalpies. I have attached a very small worksheet regarding bond enthalpies. Please solve it and hand it back to me by midnight tonight. Thank you for watching.